Hello, everyone, and welcome to Practice Applying the Rules of Random Variables, AP Questions, Day 1. So now that you know the rules of random variables, it's time to apply the rules. So let's review the rules that we went over the last few days. Rule number 1, the rule of linear transformations. Remember, a linear transformation is one, like, for example, the line y equals AB, a plus bx, where a is the y-intercept and b is the slope. Let's say I have random variable x, and I wanted to find a linear transformation of a plus bx on random variable x. So let's say I added a and then multiplied b to every x, okay? What would happen to the mean of the new random variable? Let's call it y. Well, the mean of the random variable y will be the same, we'll do exactly the same thing that you predict is going to happen. You're going to multiply the mean by the b value, whatever that is that's being multiplied, the constant that's being multiplied is b, and you're going to add the constant a. So whatever you think you predict is going to happen to the mean is what will happen. When you multiply everything by x, the mean gets multiplied by x. When you add everything by a, the mean gets added by a. Very straightforward. But standard deviation, remember, is not the same. So remember, when you multiply a constant b, it will indeed get multiplied and the spread will get bigger. But if you add a number to everything, the standard deviation remains the same. So that letter a just drops out. So that is the trickier of the two rules there to remember. Now, the other rule that we went over was combining two random variables together. So let's say we're combining variable x and y. And let's say we're talking about means. Remember the mean of x plus y, if you added every x and y together individually and then found the mean, it's the same as adding the mean of x to the mean of y, or subtracting. But with standard deviations, it does not work the same. So you cannot add the standard deviation of x to the standard deviation of y. In fact, what you have to work with instead is variance. So you have to square each individual standard deviation x, standard deviation of y, square them, add them, and then to get this, that's the variance, and then to get to the combined standard deviation, you square root. So just remember that whether you're adding or subtracting the variables together, it doesn't matter because it will become addition when the negative squared become positive. You'll get the standard deviation of the combined random variable. Okay, all right, let's go. So here is an AP question, an old AP question, but it did involve random variables. So it says, and this is in your classwork, by the way, it's called Rules of Random Variables Practice. There are 4 runners on the new high school team. The team is planning to participate in a race in which each runner runs a mile. The team time is the sum of the individual times. So let's underline that. The team time is the sum of the individual times for the 4 runners. So you guys know if you're on the track team, if you run a relay, that you all have to combine to get a team relay time. So you all may run your individual laps at different times, but then together your combined time is the team time. So remember that. Assume that the individual times are independent of each other. This is important because if they're not independent, we can't apply the rules of standard deviation, especially for the combining the random variables together. The individual times are approximately normal. Let's underline that. It's probably important with the following means and standard deviations. Okay, so separately we have runner 1, runner 2, runner 3, runner 4. They're all each individually approximately normal. So the shape of all of them is approximately normal individually. The mean is the center, and the standard deviation is the spread. So you're getting all the information about each individual runner here listed separately. Part A, runner 3 thinks he can run a mile in less than 4.2 minutes. Is this likely to happen? So this is actually a review from chapter 2, normal curve. So can you find the probability? Likelihood means probability, right? Can you find the probability that runner 2, we'll call it X, runs less than 4.2 minutes? So you guys are going to do a little normal CDF action there or Z-score action for that and find your answer. So do that now. Just spotlight runner 2 and do the bell curve for runner 2. And find the area to the left of the 4.2 for me. Okay, so I just want to remind you, if you want to get full credit on the AP and you choose to do the calculator method, which is second bars to normal CDF, you do have to write down that the values are approximately, the distribution is approximately normal, which is the shape, with a mean of 4.7 and a standard deviation of 0.16. And I do recommend that you still draw the picture, put the mean in the middle, shade the area of interest, and then you can write the probability statement, which is right here. The probability X is less than 4.2 equals, and then you can write your answer from calc. I use table A because I did the Z-score, and I got negative 3.125 for the Z-score. And when I did it, I looked on the table A, and I got 0.0009, which is very, very tiny. So is this likely to occur? I'm hoping you said no, it is unlikely to occur because the probability is very, very small. Okay. Because the probability is very small. I know I should just do a separate page for this answer. Part B, the distribution of the team times. Okay, so this is where we get into the combining, okay? Team times, underline. What are the mean and the standard deviation of the team times? All right, so remember the team means the total. Total means adding the times up of all 4 runners. So let's go to the next page for this. We're going to write mu of t, meaning mu of team. We're going to do the mean of runner 1 plus the mean of runner 2 plus the mean of runner 3 plus the mean of runner 4. Are we allowed to add up the means? And the answer is yes, you are, because you're allowed to add means together. You can just add these 4 up and you'll get the mean of the team times. So do that now and tell me what you get. So I'm hoping when you added these up, you got 18.9 for the team mean. I should really write out the work here. 4.9 plus 4.7 plus 4.5 plus 4.8 and show that the mean of the team times is equal to the sum of the individual means. Okay, so that's that. Standard deviation. Are you allowed to add the standard deviation of 1 plus standard deviation of 2 plus standard deviation of 3 plus standard deviation of 4? I'm hoping you're going to say no, you cannot. So what do you have to do instead? You have to find the variance. Okay. So first, what you're going to do is you're going to go to this column here, which I will circle, and you're going to square. You're going to square everything here and create like a variance column if you want right here. Let's do a different color. Let's do blue. Variance. Okay, so you're going to do 0.15 squared, 0.16 squared, 0.14 squared, and 0.15 squared. So do that now. And then what you're going to do is you're going to add those all up. Add them all up. And that's going to be the team variance. And then whatever you get, you're going to take the square root of that. And that's going to be the team standard deviation. So do that now. Okay, so I added them all up and I squared each one individually to get the variance of runner 1 plus runner 2 plus runner 3 plus runner 4. And I ended up getting this 0.0902, and then I took the square root of that, and that was my standard deviation. So now I have the center of the team and the spread of the team. And actually, I also have the shape, because if the individual runners were approximately normal, then the shape of the team times are also going to be approximately normal. So the shape of the team times combined are going to be approximately normal because they were all individually approximately normal. The mean of the team is going to be 18.9 minutes, and the spread of the team is 0.3003 minutes. So now I can describe the team. I also want to mention that I just looked back at my part A and realized that I did runner 2 instead of runner 3. So I should have done runner 3. So that's going to change my answer because runner 3 instead of runner 2 is going to have a different mean and standard deviation. So I just want to make a note of that. You can go back into runner 3, and that's really going to be the real answer for part A. So I apologize for that. Now let's go to part C. Suppose the team's best time to date is 18.4 minutes. So this is a team time, all right? What's the probability that the team will beat its best time? So here again, we have the word probability, which is the same as likelihood from part A. Remember in part A, we were supposed to get the probability runner 3 gets less than 4.2 minutes. So now this time we're interested in the probability that the team will beat its best time. So beat means get a time less than its best time, right? Okay, so because we said in the last part that the team shape is still approximately normal, and now we know the mean and the standard deviation of the team, we can still do a z-score, but it's going to be a z-score for the team time. So basically we can just make a new distribution called the team distribution. This is going to be the mean of the team distribution, which will be centered at 18.9. And we want to know if they can beat their best time, which is 18.4, which happens to be on the left. So now we're just going to shade to the left. And now you're going to do a z-score for 18.4. But instead of using any of these individual data, you're going to use the mean of the team and the standard deviation of the team. Okay, so find either the z-score now for 18.4 and then find the area to the left, or do the normal CDF. Okay. Okay, so I did the z-score by hand. I got negative 1.67 and I got an area of 0.0475. If you use normal CDF, I think you're going to get a little bit different because it's actually going to be more accurate. You're going to get closer to 0.048. Either one is acceptable as long as, again, you state that the distribution of the team is approximately normal for shape. You state the mean and the standard deviation of the team, and you write the correct probability notation statement, and then you write your answer. So anyway, that was a question that I spent about 12 minutes on, which is how long you want to spend, approximately 12 minutes for your response. And it went over review from chapter 2, which is normal curve, and then it incorporated teams, so combining more than one distribution and finding basically a new mean and a new standard deviation. So I like it because it's a nice combination of old and now. If you look at this next question also is kind of a combination of old and new. The first part is asking you to find the mean and the standard deviation of C, which is the probability distribution of the number of child tickets purchased for a single customer who's going to a concert. So you guys know how to do this from the past week or so. So you're going to find the mean of C and the standard deviation of C using the formulas from the reference sheet. And then remember, you can put the data in calculator in L1 and L2. You can go to stat, go over to calc, and choose one var stat. But you just have to make sure if you do this method that you do L1 and then you do L2 for the frequency list. However, on the AP, they do not want you to write that down. They want you to actually show the formula from the reference sheet, show the number plug-in, and then write the answer. So just a quick reminder, if we're doing the mean, that we would write E of X, which means expected value. I don't know why I wrote a sigma. It should be E of X equals mu of X equals sigma xi times pi. So multiply every x by its respective probability and add them up. And if you want, you only have to do the first term, which is 0 times 0.4 plus ... and then the last one, 3 times 0.1. So that's going to be the formula for the mean. Write down your answer. And then separately for the standard deviation, we'll do on the next page. Remember, the formula for standard deviation is you take every x, you take away the mean that you just got, you square it, and then you multiply it by its respective probability. You add those all up, and then you take the square root of that. So if we were to do that for this question, we would just do the first term, 0 and 0.4. So we would do 0, which is x minus the mean that we just got, square it times 0.4 plus dot 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 plus last term was 3 and 0.1. 3 minus the mean, square it times 0.1. Okay, and then eventually we'll square root that. So right now, I want you to go get the mean and the standard deviation. Do it now and write down your answer. So when I did this, I got a mean of 1, and I got a standard deviation of 1 as well. So this means that if we took many customers, we can expect that each customer will purchase about 1 child ticket per customer, and that number will deviate from the mean by 1 ticket. Okay, so we should put ticket in. So the mean is 1 ticket per customer, and this deviates from the mean on average by 1 ticket. So that's part A. This is review. Okay, so now we go on to part B and C, and here's where we get into the rules of random variables. So let's read B. Suppose the mean and the standard deviation purchased by a single customer are 2 and 1.2 respectively. So the mean and the standard deviation of adult tickets, I should underline that, are 2 and 1.2. So the mean is 2 for adult, and the standard deviation is 1.2 for adult. Assume that the number of child tickets and adult tickets purchased are independent. That's important. It means we're going to have to combine them. Impute the mean and the standard deviation of the total number of tickets of child tickets and adult tickets. Okay, so now we have 2 separate random variables here. We have child tickets, which are right here, and we found the mean and the standard deviation for child tickets in part A, which was 1 and 1, and we have adult tickets, which are cited in part B to have a mean and a standard deviation of 2 and 1.2 respectively. So if we want to find the total, thinking about a family here, total, let's call it T, we're going to have to do child plus adult, right? So the child tickets, we know, had a mean of 1 and a standard deviation of 1. The adults had a mean of whatever they told us, and a standard deviation of whatever they told us. So 2 and 1.2. Okay, so if we want to find the total of C plus A, can we add the means? And I'm hoping you're saying yes. So the mean of C plus A is equal to the mean of C plus the mean of A. 1 plus 2 equals 3. So this means that if we took many customers, we can expect that the average customer will buy 3 tickets total. Now, can we add the standard deviations? I'm hoping you're going to say no. So the next thing you have to do is find the variance of C, which is 1 squared, which is 1. Find the variance of A, which is 1.2 squared, whatever that is. And then you're going to find the variance of the combination, okay? So you're going to do the variance of C plus the variance of A. So it's going to be 1 squared plus 1.2 squared. And whatever you get is going to be your combined variance. And then you're going to take the square root of that, and that's going to be your standard deviation. So do that now. Okay, so I'm hoping that you got 1.562, or I hope you got the square root of 2.44, and that was 1.562. So this means that on average, the number of total tickets will deviate from the mean number of tickets by 1.562 tickets if we took many customers. Okay, now let's go on to part C. Suppose each child ticket costs $15. And each adult ticket costs $25. Compute the mean and the standard deviation of the total amount spent. Okay, so now we're incorporating another component here, which is cost. So what do you think you're going to do with the numbers 15 and 25? You know, think about your family. If you have 2 children and 4 adults, what are you going to do with that $15 and $25? I'm hoping you're going to say multiply, right? So that is what we're going to do. We have to definitely multiply. But what are we multiplying, right? We want to find the mean and the standard deviation of the total. So what you want to do is think about, you're going to take $15 and you're going to multiply it by every child ticket, right? But you're going to really multiply it by the mean of the child plus $25. You're going to multiply that by the mean of the adults. And that's going to be your total for the means. So the mean of the child tickets that we sold was 1. So you're going to do 15 times 1 plus 25 times, it says it above, 2. And you should get the total cost, the mean of the total cost. So this is really the mean of 15C plus 25A. It equals 15 times the mean of C plus 25 times the mean of A, if you want to do it notation. So we're going to end up getting 15 plus 50, which is $65. So we can expect that we took many, many families or many, many customers, that the average customer is going to spend $65 on their purchase total. Okay, now standard deviation. So can we multiply standard deviations by the 15 and the 25? Okay, so this is where it gets a little interesting. We can do, put a question mark, we can do 15 times the standard deviation of C. Okay, we can do 25 times the standard deviation of A. But are we allowed to add those two standard deviations together, question mark? And the answer is we're not, because we're not allowed to add standard deviations, okay? So we can get the separate standard deviations, but then what are we gonna have to do with them? We're gonna have to square them to get the variance and then square root to get the standard deviation. So that's where it gets a little ugly, okay? So you're gonna do 15 times your standard deviation of child, which is 15. You're gonna do 25 times your standard deviation of adult, which was 1.2. And we're going to get whatever we're going to get. And then what we're going to do is we're going to square those to get the variance of the child and the variance of the adults. And then we're going to add them together. And then we're going to square root. Okay. So do that now. Do 25 times 1.2. Sorry. 25 times 1.2. And then square that. And then add them together and then square. So I'm hoping that you got the square root of 1,125, which equals 3354. Okay, so again, I just want you to see again how these free response questions combine things from the past with new things. So we have finding the mean and the standard deviation of a single discrete random variable in part A, but then we're incorporating combining two random variables together in part B, adults and children, and then we are incorporating multiplying, which is one of the first skills that we discussed in the beginning, multiplying by a constant from a linear transformation. So where it gets sticky is knowing that you cannot add standard deviations. You have to work with variances. And if you memorize that, you're in good shape. Good job.